Okay, this lesson we are going to talk about these things called two-dimensional figures. When we talked about a point, that was kind of like 0 dimensions. And let's do this. Let's draw it. Okay, so here was a point. We would say there's 0 dimensions here because you can't really move. Once you're on a point, you can only stay on that point. Anytime you move in any direction at all, you're going to be somewhere else. You're not going to be on that point again. Now it looks like if we enlarge that, it looks like, that point, you could travel. Looks like you could travel from here to here. But remember, when we draw that little dot on a piece of paper, or in this case on the computer, that dot represents just one particular place. That means if you just move as short a distance as you could possibly imagine, you would be somewhere else. You would not be on this point. So that's 0 dimensions. And then we had a line, and a line is in 2 dimensions. Okay, it's just going this way and that way, all right, if you want to call it that. It's only 2 dimensions. Actually, I'm sorry, I lied. That would be 1 dimension because you can't go up and down. You're only going in one direction, either this way or this way. You can only go in one direction. As soon as you start going in another direction, you're off the line. You're not on the line anymore. So 0 dimensions, 1 dimension. And if you had 3 dimensions, that would be the one that kind of looks like, I'm sorry, 0, I can't count. Here I go again. 0, 1, and 2. This would be 2 dimensions. All right, you could go this way, or you could go this way, and that would be 2 dimensions. And that's what we're going to concentrate on today, is the 2-dimensional figures. And it's not necessarily going to be a plane, but it will be something that you can travel in 2 directions. All right, so the first word that we are going to discuss is a word that we're going to use a lot in the rest of the year, really. Okay, and that is a polygon. Poly means many. The gon refers to the angles. So basically it's a figure with many angles. So let's do this. I just took a picture of this little chart that's in the book. So this is straight from the book, literally straight from the book. And this kind of describes what a polygon is. So I thought it would just be easy, instead of me writing it all out, just to kind of point some things out to you about this. Let's go to a color that's not on here. Let's go to a green. Okay, here we go. So let's see what a polygon actually is. It's a closed figure. If it's closed, there's no gaps in it, okay? Formed by a finite number. Finite means it doesn't go infinitely. There has to be a number of sides that actually stops. So by a finite number of coplanar, remember coplanar means in the same plane, segments, remember segments has endpoints, a beginning and an end, that they're called sides, such that these things must be true. So what do we have so far? It's a closed figure, there's no gaps in here, finite number of sides, you can count how many sides there are, it doesn't go infinitely, and it's the number of segments are coplanar, okay, formed by a finite number of coplanar segments. So each of these segments is on the same plane, and you can count them up, and they're segments, they have a beginning, they have an end, it doesn't keep on going forever in any direction like this, okay, and these are all called sides. So this thing right here, GH, that's a segment, notice, line segment, that's why they put that little line over top of it, but we call that the side of a polygon. Now where they come together, where the 2 segments actually join and come together, we call the vertex. And depending on which letter it is, that's what they call this vertex J. Of course, this would be vertex K, vertex L, and so on. All right, so it's got a bunch of different sides. You could count them up. There's a finite number, so you can always count them up. 1, 2, 3, 4, 5, 6. So there are 6 sides to this polygon. Let's see what else has to be true, okay? Because there's some things that kind of look like a polygon and kind of fit with what we've described so far, but aren't necessarily a polygon. And we're going to see those in a sec. Look at this. It says such that. So these are some things that have to be true about a polygon. The sides that have a common endpoint are non-collinear. What does that mean? The sides that have a common endpoint. So for instance, like GM and GH, they have a common endpoint, which is G right there. And it says the sides that have it are non-collinear, which means they don't lie on the same, let's see, such that the sides have a common endpoint. The common endpoint are non-collinear. So let me think of what they're saying right here. Okay, basically what it's saying is this segment and this segment right here can't lie on the same line. See, they lie on different lines, okay? Because if they lie on the same line, it would just be the same exact side. All right, it's kind of it's kind of it's kind of wordy just to basically say that they have to be two separate lines, okay? It says each side intersects exactly two other sides, but only at their endpoints. So this side right here, like GH, it intersects what? Exactly means not more than, not less than, but exactly two other sides. So GH intersects this side, HJ, and it intersects this side, GM. It does not intersect any more or any less. Exactly two sides. Okay, and they intersect where? At the endpoints. It's not like this thing right here intersects halfway through and this part's hanging over. All right, you can't do that. Intersects at the segments. So it's a little bit technical on this. You'll see in a second here some examples of things that are polygons and things that are not polygons. We already talked about the vertex. It says the vertex of each angle is a vertex of the polygon. Actually, we didn't mention that. The vertex of each angle. So watch this. Angle HGM, that's that angle right there. The vertex of that angle is the vertex of the polygon. So this is the vertex of angle HGM, and it's also a vertex of this particular polygon. Now there's 6 of them, okay? So this is a vertex of this angle right here, angle GHJ, and it's also a vertex of the polygon. Again, they're getting real specific. We probably don't have to know all the little tiny details in here, right? They're just describing, but they do have to be particular because there are some things that are not polygons that kind of look like they might be, all right? It says a polygon is named by the letters of its vertices and then written in order of consecutive vertices, which means you don't skip around. So for instance, the way they named it, and they just write the word polygon, okay? There's no symbol or anything like that. You just write the word polygon, and then you start at any point. It doesn't matter what point you start at. They decided, okay, let's just start at G. And it actually doesn't matter which direction you go. You could start at G and go this way, but you have to go to consecutive vertices, which means the vertices, I don't think I've said this, vertices is the plural of vertex, okay? You're saying, what word is he saying? It's the plural of vertices. So I have one vertex, but I have 2 vertices. Hope that makes sense. All right, let's start that again. We named the polygon. We started at any point. I could have started anywhere. It doesn't matter. They just happened to start at G. All right, so they started G, and they said, okay, let's go in this direction, like this. You could have gone down this direction, but you have to go to the consecutive vertices, which means this. You have, if you start at G and you go to H, then you have to go to the next one. You can't call this G, H, L, okay, M, and then skip over to K. Or you can't do that. You got to go around the horn, sometimes I like to say. Right? So you go around the polygon, and that's what it means by the consecutive vertices, which means the ones that are right after the other one. So it goes G, H, J, K, L, M. It's a weird name for this polygon, but that's really the only way we can name it is by using the vertices on this polygon. I could have named it a whole bunch of different things. I could have gone backwards. I could have called it GMLKJH. Put polygon in front of it. I could have called it that. I could have started at any of these letters. I could have started at letter K and gone either way. But if I started at K, I would have to call it polygon KLMGHJ, or I could go backwards. I could call it polygon KJHGML. All right, hope that makes sense. It's like alphabet soup after a while. All right, so that's basically what a polygon is. Probably took way too long describing what a polygon is, but we're going to be using them so much. I think it's important that we understand what a polygon is by its definition. Now let's do this. Let's put this picture on here. This is in the book as well. And I just want to show you some examples of things that are polygons that are not polygons. And you can go back and check the specific definition of a polygon to see if it matches and if it doesn't match. Let's go red on this. Look at this. See the vertices? It's got vertices. The sides all meet at a point, right? These are the vertices of it. They all meet at a point. It does it for every single one of these. Even weird looking stuff like this. There's no gaps in it. There's no curves, all right? You can't have any curves in it. There's no openings or any gaps, anything like that. It doesn't hit, like one of the sides doesn't hit like halfway through the other one. There's no like overhanging segment, okay? It hits at the endpoints. All that stuff we talked about polygons is true about all of these, all 6 of these. Let's look at some things that are not polygons. Okay, if you take a look at this, why is this not a polygon? You say, well, look, they all meet. There's no gaps in it or anything. But why is this not a polygon? Well, you've asked a very good question. Let's scooch up a little bit. And let's move this thing a little closer to here so we can see the definition in this thing right here by itself, okay? Why is this not a polygon? Well, let's see. Each side intersects exactly 2 other sides. So let's take a look at this side right here. If we consider that one of the sides of the polygon, how many places do that intersect? Well, look, this line right here, do you see what I'm pointing at? Intersects here, and here, and where else? And here, okay? At 3 different sides it intersects. It intersects this side, okay? Intersects this side, and it intersects this side. That's 3. This says it can only intersect exactly 2 other sides. That's not a polygon. Okay, this one has a gap in it, all right? Because the, let's see, we're up here. The sides have a common endpoint. And look, do these sides have a common endpoint right here? No, they don't. It doesn't have any. It doesn't meet any other side. You got that gap in there. Look, this is like a wavy thing. These have to be segments, line segments, and that's not a line segment. A curve like that is not a line segment. Look at this one right here. This comes and meets right here. Remember, they're supposed to meet at the vertices. They have to meet at the vertices. See, but only at their endpoints. They have to intersect at the endpoints. This little thing right here does not intersect at this line segment's endpoint. Now, if I took this and I stretched it all the way to here, then that would be a polygon. But right now, it's not. This has got a curve to it, so it's not a polygon. This is like an ellipse. This is not a polygon as well. All right, so I hope you understand the difference between something that is a polygon and something that is not a polygon. And all right, let's look at a couple different types of polygons. Here's a polygon right here. Let's make this a little bit bigger. There we go. And this type of polygon is going to be called a convex polygon. This is a convex polygon. Why is it a convex polygon? Well, watch this. If you took these segments, and let's say we extended it out, okay, so we took this segment, actually, you know what I can do? Let's ungroup this. I got these all grouped together. And watch this. If I took this side and extended it out, see that? I extended it out here, and oops, I messed up. Hold on. Let's try this again. It's not doing it. All right, give me a chance here. No. Hold on. Okay, that extended out. Well, let's do it to this one. Okay, if I took this and extend that out, I don't know why the other side's not extending. Took this and extend that out, and this one, and this one, and this one. Okay. Now watch. If you did that, if you extended all these sides, look at where all those extensions go. All those extensions, and I should be able to extend the other side out. I don't know why that's kind of bugging me. Oh, there we go. Why didn't it do it before? Oops, and then it jumped up there. Sorry, I'm experimenting at your expense, aren't I? And I know you want to get done this. There we go. For some reason, I wasn't able to get it to do it. Now it's working. All right, see what I'm doing? I'm extending all the sides. Now, what I want you to see here is if I extend all the sides of this polygon, none of those extensions are going to intersect inside the polygon. All right, it's kind of like a test. And extend this. I don't know why I couldn't have done it before. So there I did it, finally. I extended all the sides of this polygon, and look where they extend. They all extend outside of the polygon. None of them actually went inside or the interior of the polygon. If I do that to whatever polygon I have, that's going to give me a convex polygon. So this is convex because I extended all the sides and they all extend outside of the polygon. Nothing is inside of there. See, it's clean as it was when I first started it. All these extensions go to the outside and eventually they're going to intersect. Look, those, if I extended that far enough and far enough here, that would intersect. If I extended this a little bit more, they would intersect. Okay, same thing with all these. That would intersect this one. These two would intersect. These two right here would intersect. You get the idea. So if I extend any of the sides, they'll all intersect outside of the polygon. We call that a convex polygon. Well, I said there was two types. Let's look at the second type. Let's push this down a little bit. I'll make this a little bit bigger. And we're going to kind of do the same deal with this. All right. But what I want you to see, and let's ungroup it so I can deal with all the individual segments. Okay, so watch. If I took this and I extended this side, and then I took this one and I extended that side. So far, everything's outside, isn't it? And I extended that side, and I took this one, I extended that. Oops, messed up a little bit. Gotta be a little more careful. Okay, there we go. And I extended that, and I extended that. Everything's good so far. Look, everything, all these extensions, even this one right here, watch. If I extended that, it all goes outside. But watch this part. If I took this one right here and extended it, what's it doing? It goes through the inside, and the same thing with this one. See that? It goes, I think that's right. Yeah, it goes inside of the polygon. Remember, the polygon was nice and plain. There was nothing going inside it. But all this is inside the polygon, and all this is inside the polygon. So this is not a convex polygon. We call this a concave polygon. Probably spent too much time on this because we don't really deal with this all that often. But every once in a while they'll ask you if it's convex or concave, and you kind of need to know. All right, so that would be a concave. When I think about a concave polygon, let's put the polygon up here like it was before. Do you see how this kind of bends in towards the polygon right here? So it's concave. It kind of bends in. I think of a cave when, you know, you like you're hiking or something, you see a cave, you go inside the cave. So this is kind of like the opening to the cave. Does that kind of make sense? That's how I remember anyway, that it's a concave polygon. Now we have a basic understanding of polygons. What we're going to do here is we're going to take a look at certain polygons with a certain number of sides on it, and we're going to give it some names. So here's, again, straight from the book. And let's take a look, and we're just going to name the polygon by how many sides it has. So if it has a certain number of sides, we're going to give it a certain name. So if you look at it, if you have 3 sides, you're going to call it a triangle, and you've heard of that. Tri meaning 3. These all have prefixes that represent this number. 4 is a quadrilateral. A lot of people say, oh, 4-sided, that's a square, that's a rectangle. Not necessarily. We call it a quadrilateral. The lateral part means sides, the quad means 4 sides. Okay. 5 is a pentagon. You probably heard of a pentagon, which is the big old building in Washington, D.C. It's the Pentagon. Why? Because it's got 5 sides. Hexagon is 6 sides. Hexa is prefix for 6. 7 sides is a heptagon. You don't see 7 all that often. 6 you see a lot. 5, 4, 3 you see a lot. 7 not so much. 8 you see probably every single day. And what is it that has 8 sides that you probably see every single day? At least if you're in a car or something like that. Yep. Let's see, put it on here. Yep, you're right. It's a stop sign. So a stop sign is an octagon. Count them. 1, 2, 3, 4, 5, 6, 7, 8 sides. So 8 sides is an octagon. Let's see this. Oh, did you know a soccer ball is actually made up? Well, it depends on how they stitch them nowadays. When I was in high school, all the soccer balls kind of look the same, and there's actually a combination of pentagons and hexagons. I think they still make them like that, but now they've kind of got a little extra fancy on the soccer balls. So let's take a look at a soccer ball. This is like an old-fashioned soccer ball. They still make them like this? I guess they do. So let's take a look. Let's count the white ones. Count the sides for all the white blocks. I don't know if you even realize this, but watch. 1, 2, 3, 4, 5, 6. So that's a hexagon. All the white ones in here are hexagons, 6 sides. Look at the black ones. Let's do this one. 1, 2, 3, 4, 5. So all the black ones are pentagons, and all the white ones are hexagons. I don't know if you knew that or not. I thought that's kind of interesting. They actually do that for a reason, because in order to make this ball, this sphere, these angles match up real nice and perfect to do that. Now they got fancy ones where the stitching is all kind of wavy and all that kind of stuff. But yeah, the old-fashioned soccer balls was a combination of a hexagon and a pentagon. Thought that was kind of cool. All right, let's keep going. Where were we? We did octagon, right? Nonagon, 9 sides is a nonagon. I don't see those very often, but that's what they call it, a nonagon. 10 is a decagon. That's pretty popular because deca means 10, the prefix, like decade, all right, or a decimeter or something like that. It's all 10. So deca is 10. Hardly ever heard of this one before. Hendecagon, okay? You don't hear about 11 sides very often. It's a little odd type of number, but that's what they call it right here. Hendecagon. 12 is kind of cool sounding. It's dodecagon. 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 That's 12. Now, they don't have numbers for every single, like if you have 57 sides, they don't have a special name for that polygon. So we just call it how many sides we have. So we wouldn't call a 57-sided polygon an n-gon. We would call it a 57-gon. Or I probably wouldn't even call that. I'd probably say, well, it's a polygon with 57 sides. That's probably what I would say. All right, so know these. All right, know these words right here. Again, a couple of them I hardly ever use, like heptagon and hendecagon. Even nonagon, you don't use that often. But all the other ones are used quite often, so it's good to know what the names of those are. Okay, continuing with naming certain types of polygons. I've got a polygon right here. Let's make this a little bit bigger. It's pretty good. Now there's something special, a little bit more special about this polygon than what we've talked about before. If you take a look at this polygon, I'm not going to measure it, but if you wanted to, you could. If I measure this side, this one, this one, this one, there's 5 sides, so it's a pentagon. But if I measure them, all the lengths of all 5 of these sides are exactly the same. So what I could do, remember we talked about the tick marks? I could put a tick mark here, 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 and here. So I could say that all 5 of these sides are actually equal to each other. That doesn't have to be true about every single polygon, but on this particular one, it is true. Do you see anything else that might be true about this? Well, look at the angles. If I was to measure all these angles are exactly the same. So I can put one arc for each of these angles, and that represents that all the angles are equal to each other. So if you have a polygon and all the sides are equal to each other and all the angles are exactly the same, they're all equal to each other, I call this thing a regular polygon. And we're going to do stuff a little bit later on, not in this lesson, but a little bit later on. We're going to do some stuff with a regular polygon. It involves a lot of math. Even later on in the book, we're going to do some stuff that is going to have some trigonometry. Okay, that's a lot later in the book, towards the end. So knowing a regular polygon is very, very important. But right now, all you have to know on a regular polygon is that all the angles are equal to each other and all the sides are equal to each other. All right, you could have any number of sides and have a regular polygon. This happens to be just a 5-sided figure, and that would be a regular polygon. Or I could call it, instead of just calling it polygon, since I know how many sides, you could call it what? A regular pentagon. So if they say a regular pentagon, it looks like this. And in fact, remember we talked about the building in DC? That's actually a regular pentagon because all the angles are the same and all the sides are the same. Go ahead to Washington, take your tape measure and measure all the sides of the buildings. Well, don't actually do that. That'd be kind of silly. But that's what it is in DC. It's a regular pentagon. Okay, here we are again, another lesson chock full of information. There's so much stuff in this lesson right here, so I am trying to go quick, but man, we got to hit the stuff, okay? So if it takes a little bit longer, then it takes a little bit longer. But let's talk about this. Now, these are still polygons. We're still talking about polygons, and this is stuff you probably did back in middle school, all right? We are going to discuss perimeter, circumference, and area. Let's just talk about perimeter. The way that I remember perimeter and the way that I teach my students perimeter, I just use 2 words to describe perimeter. I say it is the distance around. Around what? Well, whatever you're trying to find the perimeter of. Okay, so whatever the object is, in order to find the perimeter, it's just the distance around. Basically, you just add up the lengths around this perimeter. Now, they give you these fancy, see this right here and here and here. They give you these fancy formulas for perimeter. I really think it's kind of a waste of time to try to memorize these formulas. There's no way. I'm not going to sit there, okay, what was perimeter? It was B plus C plus D. No, I'm not going to remember that. What I'm going to do, if I want to find the perimeter of a triangle, I'm just going to add up the sides of the triangle. So if I know this side B or C and B and D, what am I going to do? I'm just going to add them up. Do I have to really memorize this formula? No, absolutely not. Same thing with a square. You know all the sides of a square are equal to each other. You knew that from elementary and middle school days. All I do is just add the four sides together. What about a rectangle? Same thing. Add the four sides together. It's not like you have to memorize 2L plus 2W. There's no way. You don't have to worry about that. It's just adding the sides together. All right, so I wouldn't memorize those formulas for perimeter. That's what the P stands for. Now, on a circle, though, it's a little different, okay, because that's not really intuitive. So what I would do, I definitely would memorize the circumference. Now, on a circle, for some reason, they like to give fancy names to the circle. So the word circumference, right here, the word circumference means perimeter, but it's the perimeter of a circle, okay? They use circumference when they talk about circles. They have a different word for it, but you could say the perimeter of a circle if you wanted to. But let's just memorize it. I'm not going to talk about pi right now. Maybe another time I will. But you know what pi is. It's 3.14, 3.14, and that's what we're going to use. Don't use 22 over 7. Use 3.14. All right, so pi, it's approximately, it's not exactly, but it's approximately 3.14. Usually I do a little demonstration and talk about pi, maybe another time, not today. So the circumference is 2 pi r. What is r? R is the radius of the circle. There's a point at the center of the circle and it comes out to and meets the circle. That is the radius. Now if you look at this, the radius, if I take 2, and the plural of radius is radii, if I take 2 radii, okay, that makes 1 diameter. So for instance, from here to here would be a radius, and from here to here would be a radius. It took 2 of those radii to make 1 of these diameters. So watch, there's the 2 and the r. What's 2 radii? Is 1 diameter. So you could memorize it both ways. You could memorize it 2 pi r, or you could memorize it pi times diameter. It just depends on what they give you in this. All right, let's go to area and we'll be finished with this. Maybe we'll do an example or two. The triangle, again, this is all under triangle. Now this is something that you definitely want to memorize. I'll show you maybe another time how they came up with this, just because I'm running out of time and I want to keep this close to 30 minutes as much as I can. Okay, so just memorize this for the area of a triangle. The area is how much stuff is inside the triangle. Okay, it's all of that. It's basically what it is how many squares can you fit inside a triangle. Again, there's another chapter that deals, a whole chapter that deals with this stuff, and I'll get a lot more technical when we get to that. Right now, I just want you to learn how to use these formulas. All right, so how do you do this? It's 1/2 the base times the height. The base is the bottom of it. The height is this one right here. I know you can't see it real well, but from here to here, all right, it's actually perpendicular to the base. The height is always perpendicular. Notice they put that little perpendicular box right there. So the height is always perpendicular to the base. So how do you find the area? You take the base times the height and you take half of it, or you just divide by 2. Some people would write it like this. Base times height divided by 2. They're both the exact same thing. Okay, look at this, the area of a square. Well, if you can remember the area of a rectangle, to tell you the truth, you don't even have to memorize. Don't even memorize this, because a square basically is a rectangle. It's just a rectangle with all 4 equal sides. So what we're going to do is just memorize the area is the length times the width, right? See, that would be a length and that would be a width. They're both exactly the same. S times S is S squared. That's how we get that. But just memorize one formula and it shoots both of those down. All right, so area is length times width. Doesn't matter which one you call the length, which one you call the width. Just one side is the length, and the different side, the other side that's not the same length, that's the width. This is length, that's width. Multiply them together, and that's the area. I kind of really flew through this. Oh, I almost forgot. On a circle, the area is pi r squared. You square the radius, so whatever the radius is, you square it, you multiply by itself, then you multiply that by 3.14. That's the area of a circle. Again, I hate flying through this. This really takes like a whole lesson to really give this what it's worth, okay? I just kind of flew through it because they're not really going to stick with it too much. They're just going to be real basic. Just know some of these formulas and you'll be good to go. So look what I circled. Know this one. Know that the perimeter is the distance around something. Know the area of a triangle is base times height divided by 2. You really don't have to memorize anything for the square. For the rectangle, for perimeter, just add up the sides. For area, it's length times width. Definitely have that memorized right there. Definitely have the ones with the circles memorized. Memorize this one and memorize both of these right there, okay, for the circumference of a circle. All right, let's do a couple examples and we'll be done. Okay, let's take a look at this example right here. This is not too big of a deal. It's a rectangle, and they ask you to find two things. They say find the perimeter and find the area. So we're finding two things. Now, how do we find the perimeter of this thing? It's just the distance around it. Well, I know this side and this side. I don't know these two. But if it's a rectangle, the two opposite sides are going to be exactly the same. So that's going to be 3.2. And if this is 2.1, then that's going to be 2.1. So if I wanted to find the distance around this thing, I don't have to memorize any formula. All I got to do is just add them up. So I got, let's do a little bit in our head. Let's add 3.2 and 3.2. What is that? That's 6.4. Okay, and let's add 2.1 and 2.1. That's 4.2. And then if I add those two up, that's a 6 and that's a 10. There's my decimal, and it's 10.6 centimeters. That would be the perimeter. That's just the distance around. If I was to walk, if I was to start right here and just walk around this, if it was a building, okay, and I was going to walk around it, it'd be a small building because these are centimeters, but you get the idea. If I was to take this and walk around this thing, then I would walk 10.6 centimeters. All right, let's do the area of this thing. Well, we have to memorize what the area is of a rectangle, and we just talked about it. It's the length times the width. So it doesn't matter which one you call the length and the width. It's just the two that are different. I wouldn't call this the length and this the width. They have to be the two sides that are different. So this I'll call the length, this I'll call the width. How do we find the area of this? We just multiply them together. So I take 3.2, multiply it by 2.1. Now watch, I should have put that in there. This is centimeters and this is centimeters. If I multiply them together, let's see, I'm looking in the book because I just don't want to do this. It's, let's see, 6.72. 6.72 if I multiply them together. Look at the centimeters though. This is centimeters times centimeters. If you have something times itself, it's squared, so it's centimeters squared. Area is always in square units. Perimeter is just in the units itself. All right, so the area of that rectangle is going to be 6.72. Make sure I'm looking at the right thing. Yep, that looks right. Okay, you could just round it 6.7 if you wanted to. I'm not going to be that particular, but if you, I'm just going by what the book says, it's 6.72. All right, we're finally here, last one. Okay, we're going to find the circumference and the area of this circle. So we need to know the formula for circumference. This should be memorized. You could memorize it pi times diameter, or you could memorize it, let's write it right here, C equals, or circumference equals 2 pi r, because twice the radius is the diameter. I like to use 2 pi r because what do they give you right here? They don't give you the diameter, they give you the radius. So let's just use the one with the radius in it. So let's plug some stuff in. So it's 2 times pi, which is 3.14, we'll just round it to that, times the radius, and the radius is 3. And just to make this a little easier on the calculator, 2 times 3 is 6. So really, we're going 6 times 3.14. I'll bring the calculator into this one. And so it's going to be 6 times 3.14. Now, if you notice, your calculators will have a pi button on it. Okay, I'm going to use the 3.14. Okay, let's not use the pi button. Let's just use 3.14. I believe that's what they do on the problems. So we do it. It's 18.84. They actually put 0.85. They might have used, I'll tell you what, let's do this. Let's go 6 times, and let's actually use the pi button. I have to hit second function, then this button right there. So see, 6 times pi, hit equals, and sure enough, this rounded it, right when I used 3.14, it just stayed at 4. But if I use the pi button, it's 0.849. That 9 rounds that 5 up to, or 4 up to a 5. That's why they have 0.85. I will not be that picky, okay? If you put 18.84, that's fine. If you put 0.85, that's fine, okay? I'm perfectly okay, unless I tell you to use the pi button or something. But you could go either way. You can use 3.14 or you can use the pi button. I'll understand if you're a decimal off. Since the book used 0.85, might as well go ahead and do that. Say that 9 rounds the 4 up to a 5, 18.85. So 18.85. This is circumference, it's in inches, and so we just keep it inches, because perimeter, you just keep the same unit. Let's do the area. Well, what is the area? People get confused between these two. Remember, circumference is just the units itself. It's nothing squared. Area is always squared. It's how many squares can you fit inside this circle. That's what you're finding. So it's pi r squared. Square goes with area. All right, this is just straight up distance. That goes with circumference. The squared always goes with the area. So let's plug some stuff in. So it's pi. I'll just put the pi symbol down. We'll use the pi button on the calculator. All right, it's r, which is 3, and then it's squared. So what is this? This is pi times 9, or 9 pi. Let's chuck that into a calculator. Scooch it over so we can see. So let's put 9 pi, and we'll probably stay consistent. So on this calculator, you don't even actually have to put the times button on here. You can just hit 9 and then hit second function, this button right here. See, 9 pi. And it will automatically multiply it together. So we hit equals, and you get 28 point. Let's round it to just 1 decimal instead of 2 like this one. That's what the book did. So let's round it to 1 decimal. So if I round it to 1 decimal, that 7 rounds this 2 up to a 3. So I get 28.3. So the area is 28.3. Now it's in inches, and it's area. So it's always inches what? It's squared, so we put inches squared. Don't square the 28.3, just square the inches. And that's how we write that answer. All right, I went 36 minutes, almost 37. Sorry, but man, that was a lot of stuff. So I hope that helped you out a little bit.